Hey class, notes for 19.3. There's a lot to go over here. I'm going to go through some of these slides pretty quickly, so you don't have to write everything down. I would probably write down just a couple of things I highlight though, such as we're talking about entropy. Entropy is obviously the term that's used for when something goes to a more complex system, or when something has the ability to change in more ways. We're going to try and nail this down. Entropy tends to be the confusing one. Remember, just as a review before, that when we talk about enthalpy, enthalpy was basically just heat. Now we all know what heat is, so that doesn't need much explanation. Entropy is not heat. Entropy is like something moving to a more complex state. And that's the extra part that's a little bit different. So notice that this Clausius guy, Rudolf, the best names ever, Lothar Meyer, Rudolf Clausius, Ludwig Boltzmann, who we'll talk about later on, he determined that entropy is heat divided by temperature. Now, this is something that's really kind of important to understand, the difference between heat and temperature. So heat divided by temperature, most people think that heat and temperature are basically the same thing, which they definitely are not. To give you an example of when heat and temperature are not the same thing, you should think about when you're baking a pie and you have aluminum foil over top of the pie. Okay, if you're baking that pie at 400 degrees Fahrenheit, and part of the baking instructions is to midway through pull the aluminum foil off the pie when it's in the oven at 400 degrees so the top can brown. Yes, I know a lot about this. The reason why you can use your fingers without a glove to pull the 400 degree aluminum foil off of the pie is because the aluminum foil doesn't have a lot of mass, therefore it doesn't hold a lot of heat. So it doesn't burn your fingers to pull the aluminum foil off. But of course you'd put gloves on then to move the pie out of the oven to put it on top of the stove to let it cool, because the pie and the pie plate, or whatever you're baking it in, has a lot of mass and holds a lot of heat and will definitely burn your hand, but not the aluminum foil. So heat can be, like, the amount of heat is also dependent on the amount of mass of an object. So that's important to know. Okay, let's continue on. Entropy can be thought of as the measure of randomness. That's another way to say it, measure of randomness of a system. If there's very little randomness, there's very little entropy. It is related to the various modes of motion of the molecules. We'll get into that more specifically. Let's keep moving here. Like total energy and enthalpy, entropy is a state function, which means the change, the final minus the initial. This is something that we've talked about before. Final minus initial. Okay, and it's going to act like some other stuff that we've done. So that's good. The process is occurring at a constant temperature, or isothermal means constant temperature. That's good to know. The change in entropy is equal to the heat that would be transferred if the process were reversible, divided by the temperature. So a reversible process divided by the temperature. Okay, that's just your standard. So the second law says in thermodynamics that the second law of thermodynamics says the entropy of the universe increases for all spontaneous processes, and the entropy of the universe does not change for reversible processes. So something that you can go, this would be like H2O as a solid changes to H2O as a liquid. That's an L for liquid. This is a process that is reversible. So that means the delta S of the universe, that the universe doesn't change when you go from S to liquid, from solid to liquid, which would be an increase in entropy, increase in randomness, because you can go back again from liquid to solid by decreasing the amount of heat in the temperature in the system. So that's a reversible process that does not change the universe, but something like iron solid plus O2 gives us Fe2O3, and that of course would also be a solid. This is a gas. So in this process, this is not a reversible process. at least definitely not easily reversible. It definitely works better to go in the forward direction than it does in the reverse direction. So that, of course, is not a reversible process, and there is a difference in the universe when we change those two. Okay, maybe not the best example, but you get the idea. So second law, universe is system plus surroundings. So for a reversible process, it equals 0, the entropy of the universe. But for an irreversible process, or a process that only goes forward, then it's greater than 1, okay, or greater than 0. So it continues to increase. Last truths mean the result of all spontaneous processes, the entropy of the universe increases. Okay, good. Boltzmann's constant. Okay, Ludwig Boltzmann described the concept of entropy on the molecular level. He talks about all the different ways a molecule, like a water molecule. Notice you have a situation where the two hydrogen atoms here, this is oxygen, are moving away from the oxygen atom. The hydrogens are moving away. That's one motion. Another one is when they vibrate back and forth. Another one is when one goes in, the other one goes out, and when the whole thing spins. Those are four measurements, or four types of movement for molecules. Each one of these constitutes a different way that the molecule can move, which means, which is where we're getting our understanding of randomness, because each instance of this type of motion accounts for like 1 unit of randomness. So let's continue on. We'll explain more as we go on. Translational, moving from one place to the other. Vibrational is what we're talking about down here, and rotational. So translational, vibrational, rotational, those are the 3 different types of movement. Come on, there we go. Where are we at here? There's something called microstates. So if you take a snapshot of just one molecule in its position and literally take a picture of it, instant, in a very, very short amount of time, that's called a microstate. And the more microstates you have, the more randomness you have. So the more ways a molecule can move, the more random it is. That's why, well, we're going to get into it. We will get into it. I'll talk more about what that actually means. So entropy in the molecular scale. Take a look at this. This is entropy, is signified with an S. The K, the lower k is the constant. This is Boltzmann constant. Notice that it's joules per Kelvin, which means energy or heat divided by temperature. Okay, so that's that. The K is Boltzmann's constant, and then natural log for the Ln, and the W then is the number of microstates. Now, if we're talking about molecules, the number of microstates, the specific number of microstates a molecule can have, is not easily known. But there is one way we can check it, though, because, and then of course you know the number of microstates. So the delta S is equal to final minus initial. So that's the S of the final minus the S of the initial. And because we have now, let me just go back. Because we have now this equation for it, then we can substitute in that equation for the final minus initial, and it looks like this. Now, that's not very interesting, so don't write that down. But this is what's, where are we at here? This is what gets to be the number of microstates here. This is where like the tire hits the road. The number of microstates, and therefore the entropy tends to increase with increase of temperature. So increased temperature means increased microstates. Increased volume means increased microstates. The number of independently moving particles, that means moles of the product. That's all that means, moles of the product. And we will, like, compared to minus the reactant. Okay, product minus reactant, number of moles. That then, so if the number increases, of particles, then you have an increase of the microstates, which means you have an increase of the randomness, which means you have an increase of the delta S. Okay, so that's important. So that's why we say, and I was just about ready to say this at the other slide, is that we have gas here, so the entropy of a gas will always be higher than the entropy of the same substance that is in liquid form. And the entropy of the liquid form is always going to be higher than the same substance that's in solid form. And that's because, as a solid, all translational motion, unless the whole piece moves, these individual particles do not move in relation to each other. They are locked into position. That's not the same, though, for liquids. Liquids are allowed to slide by each other, and gases are allowed to move very quickly because they're not even in contact with each other. They may bounce off each other into container walls, but otherwise they are free to move. So the more freedom you have, the more microstates, the more entropy you have. So that means, now here's what I want to point out with this, is take a look at this. Melting here has this much of an increase in entropy. So entropy increases when something's melting, going from a solid to a liquid. But notice the difference between melting and boiling. So going from a liquid to a gas is a much higher change, positive change in entropy than going from a solid to a liquid is. Okay, that was the other thing I wanted to point out. Just about finished. So solutions going from a solid, of course, to a solution is also an increase in entropy. And then, where are we at here? Gases form from liquids and solids. Liquids, so in general, the increase is when number of molecules increases, the number of moles increases. So this is all good stuff. Here's the third law, says the only time there is zero entropy is when we have one microstate. That one microstate would be at 0 Kelvin for pure crystalline solid, which means that the particles of the solid are not moving at all and the solid's not moving at all. So when that happens, that is an entropy of 0. Okay, and that's 19.4. Sorry, that was a long one.